This lecture was organized by Dr. Alemi. Among all the distributions that we see in practice, the most common is a symmetric, unimodal, bell-shaped curve distribution. It is so common that it is known as the normal distribution. Here we see a normal curve with a mean of 52 and standard deviation of 6. Normal curves are always symmetric around their mean. The portion of the curve to the left of the mean is the mirror image of the curve to the right of the mean. They are always unimodal, meaning that it has one high peak. But different variability. Here both curves have a mean of 52, but one has standard deviation of 6, another 12. And different means. Here we see two normal curves with same variability around their means, but different means, one at 76 and another at 52. Because the mean and the standard deviation describe a normal distribution exactly, they are called distribution parameters. Many variables are nearly normal, but none are exactly normal. Thus, the normal distribution, while not perfect for any single problem, is very useful for a variety of problems. Many processes are near normal. For example, as sample size increases, the average of the sample becomes increasingly like normal distribution. Here we see four distributions. First one is normal, that should remain normal. The second one is uniform. The third one is exponential, and the fourth one is parabolic. No matter what is the initial distribution, as the size of the sample increases, the average of the sample is distributed like a normal distribution. Here we see the average of two observations. Already the distribution is becoming more like normal distribution. Now we see the average of 5 observations. The symmetric unimodal shape of normal distribution can be seen clearly for the first two distributions. The average of 5 observations from exponential distribution looks not completely symmetric, but it is unimodal. Even the average of 5 observations from parabolic distribution seems a little bit wiggly, but it's getting near to a normal, unimodal, and symmetric distribution. Let's look at 30 observations and the average distribution for 30 observations. Now the number of observation averages increased. The average increasingly has a normal distribution. This makes normal distribution relevant for analysis of average of observations even when these observations are not normal. A binomial distribution can be approximated by normal distribution when there are a large number of observations. Here we see the histogram of binomial distribution of 16 patients having MRSA infection versus the same distribution curve drawn using normal curve. Normal distribution is pervasive and applies to many situations. A standard normal distribution has a mean of 0 and a standard deviation of 1. The most common value is the mean. That's where the peak occurs. (68.27% of data fall within one standard deviation for the standard normal curve. This area is marked in yellow here. 95.45% of the data fall within two standard deviations. This is the white and the yellow area under the standard normal curve shown here. 99.73% of data fall within three standard deviation of normal curve. Knowing how many standard deviation an observation is away from the mean of the distribution tells us the probability of how likely it is to observe it. This provides an easy method of understanding how unusual an observation is. An observation becomes less frequent and more unusual depending on number of standard deviations it is away from the mean. At one standard deviation, 84% of observations fall below it. At 2 standard deviations, 98% of observations fall below it. At 3 standard deviation, 99% of the observations fall below it. The chances of observing a value more than 3 standard deviation away from the mean falls below 1 in 1000. Standard normal tables exist that tell us how common a value is based on how many standard deviations it is away from the mean. To count the number of standard deviations an observation is away from a mean, we need the z-score. If the observation is 1 standard deviation above the mean, its z-score is 1. If it is 1.5 standard deviations below the mean, then its z-score is minus 1.5. This equation shows the z-score for an observation x that follows a distribution with mean mu and standard deviation sigma. While the original distribution is centered around mean mu and has standard deviation of sigma, the z-scores transforms the distribution to a standard normal distribution with mean of 0 and standard deviation of 1. Let us take a very simple example to demonstrate the power of normal distribution. Assume that patients' ratings are normally distributed and we have 3 ratings of 3, 4 and 5. What is the mean and standard deviation? The mean is 4 and the standard deviation is 1. Given this mean and standard deviations, we can now answer other questions. In this question, we are asking how unusual it is to observe a rating of 1. To answer this question, we need to calculate the z-value. The z-value is minus 3. We can now look up in standard normal tables to see what percentage of values are more than 3 standard deviations below the mean. This shows a standard normal table. The column shows the last 2 digits of z-score. The row shows the z-score to the first digit. The cells values give the percent of values falling below the z-score. Zooming in, we select for the second digit the column corresponding with 0.00 and the row corresponding with z of minus 3.0. We read that the probability of observing a z of less than minus 3.00 is 0.0013. Therefore, observing a rating of 1 is quite rare. Normal distributions allow us to examine how rare an observation is. See if you can answer this question.